Hello, hi, namaskar. I'm Prashil. I'm a Prime Minister's Research Fellow at IIT Bombay. And here we are learning chemical engineering thermodynamics, chemical reaction engineering, which that includes the thermodynamics part also when we talk about the temperature effect. And this is the live interaction session for week 2. And we will be discussing various topics in that have covered in week 2. Okay. So I'll quickly recap what we studied in previous classes. So in first week we talked about okay what is chemical industry, what is chemical industry, and to prepare large scale chemicals or to produce large amount of chemicals from these chemical industries, we need two things. One is kinetics and second is contacting. These two things are the one that decides okay how efficient your process would be, how economical your process would be for a manufacturing of particular chemical, for example ammonia. What is the best process, at what temperature and pressure we should do that reaction, so that the kinetics that tells you what is the speed of the chemical reaction, and contacting, what sort of contacting pattern you should use, for example semi batch reactor or the plug flow reactor, which we are going to discuss in detail. Okay, so these things will decide the efficiency of the project, efficiency of the process. So we draw something like this. So we have a reactor in a chemical industry. There will be input to this reactor, for example raw materials, and these materials need to be purified, right? And such processes are called as unit operations, right? Then in the reactor there is chemical reaction that is happening. And how do you know there is reaction that is happening? There are multiple indicators. For example, you mix two chemicals and the color of that mixture is changing, that means there is chemical reaction happening. You mix two chemicals and the temperature increases, that is what is an indication of chemical reaction. In real life, for example, you must have used eno, right? When you put that eno in water, there is a formation of bubbles that shows there is chemical reaction that is happening, right? So those are the indications of chemical reaction. Okay, now whenever you prepare a tea, you separate it using a filter. You do not see the change in color, right? That means there is no chemical reaction that is happening, or if it is happening, the rate is very very small, so that you do not see major changes. So those are called as unit operations, and this is unit process. This will give you output, and we discussed that output is a function of kinetics and contacting, right? Then we talked about what are the different types of chemical reactions are there. The most important criteria and most important categories by which we divide the chemical reaction or we categorize the chemical reactions are: first is based on the phases, and that's what entirely divides chemical reaction engineering into two parts. Phases, based on the phases we can have homogeneous reactions and heterogeneous reactions, right? And in case of homogeneous, as I said, there is no mass transfer limitation. That means you have two chemicals, for example gas A and gas B, which are completely miscible. And if they are miscible, the the final product that you get or the mixture that you get is also a gaseous state, is also a gaseous state. In that case, we do not need efforts for chemical A to react with chemical B, and that's why it is homogeneous. There is no mass transfer limitation. But when you talk about heterogeneous reactions, there is mass transfer limitation, right? And what do I mean by mass transfer limitation? Again, for example, I have coal and I want to burn it. I need oxygen. So for the burning of coal, if you supply heat here, oxygen is required to enter inside the coal, and there is this reactions carbon plus O2. There is a formation of CO2. So what is happening? CO2 has to diffuse inside the coal, and that's why there are two phases. Carbon is in solid phase and oxygen is in gas phase. That's where the mass transfer limitation comes. And here we divide chemical reaction engineering into two parts. One is chemical reaction engineering 1, another is chemical reaction engineering 2, that deals with heterogeneous part. Then we had exothermic endothermic reactions. This is very common. You must have studied in your undergrad or you must have seen in 12th standard itself, so I'll not go into the details. Then we talked about something called as molecularity of the reaction. We talked about, okay, what is the order of the reaction, rate of reaction, and various other things. Rate, rate constant, then molecularity of the reaction. Then we talked about order of the reaction, correct? And we have solved some questions from textbooks and question papers, for example, GATE, and those had given you clarity of what theory that we are learning. Are we able to apply those in solving problems? Okay, so now we will be talking about week 2, where we'll be discussing about, first is conversion. Meaning is that how much of chemical has converted into a product. We'll go into the details. Then we talked about limiting reactant in previous class. We have solved one example also. What is limiting reactant and how this limiting reactant is useful in getting the conversion. Okay. Then we talk about the volume change, that is fractional change in volume. This is applicable for variable volume reacting system, VVRS, variable volume reacting system, right? Then we will talk about how this can be used in continuous process or flow process. We will solve some questions and those will give you better clarity of the applications of these things in solving the reaction engineering problems. Okay, so let me see my notes. Yes, so for example, there is a reaction that is happening. A plus B gives you C plus D. Now looking at this reaction, you will see this is a toy problem, but this is what we used in real life. Okay, for example, I want to bake cookie. Okay, so what are the things that are required? One is egg, second is you need some dough, right? Or you may need some third component, For example, I want to add banana here, right? So for to prepare a cookie, to prepare one cookie, what we need, for example, 3 eggs plus for example one dough sample, and we also need, for example, okay, we will remove, oh, okay, no issues, 3 bananas, which will give you one cookie, right? So what you see, a here is 3, b here is 1, and there will be some component if present, right? And these are something that is reacting, that is interacting to form one cookie. So this toy problem can be used to study chemical reaction engineering and various other related applications, right? So now during this process, what happens when you prepare cookie, the volume of the system may change or volume of the system may not change. Sometimes if you add some soda, what happens, it swells, and the size of that bread whatever is present, it increases, right? That means I had one system, I had one reactor inside which I had prepared one cookie or cake, whatever. And then what happens after certain time, when you add these components inside, the size of the system, the volume of the system may change or may remain constant. So depending on this, we categorize chemical reacting systems into two types. One is one is constant volume reacting system, where the volume is not changing, constant volume reacting system, and variable volume reacting system, where the volume of the reacting system changes, right? And how do you identify these things? You know, from the gas equation, PV is equals to nRT, right? The number of moles are proportional to the pressure and number volume, right? So at constant temperature and pressure, which is what we see, the room temperature is 323 Kelvin, that is 298 Kelvin, which is 25 degrees Celsius, and pressure is the surrounding atmospheric pressure, right? So pressure is equal to 1 bar. So at constant temperature pressure, you are preparing a cookie or a cake, so these factors will be constant. Now can you see, n is proportional to the volume. So if the number of moles are increasing during the reaction, volume will increase, right? And that's why you need to check the total number of moles. For example, I have A plus BB, that gives you CC plus DD. This is small c. So you calculate change in number of moles. How many moles are there in the reactant? A plus B. How many moles are there in the product? C plus D. If A plus B is not equal to C plus D, that means number of moles have changed. So such systems are called as variable volume reacting system. And if it is equal, then it is constant volume reacting system. Constant volume reacting system. Correct? So based on the number of moles that are present in the chemical reaction, that are given in the chemical reaction, we call it stoichiometric coefficients. We can decide whether the volume of the reaction will change or not. Correct? For example, in a reaction where I am having 2A gives 2R. A is the reactant and R is the product. So what is happening? Number of moles are not changing. That means volume of the system will not change. And what I am talking about is PV is equal to nRT, which is a gas equation. So I am talking about gas phase reactions. For liquid, what will happen? Liquids are incompressible. Take water in a glass and try to push it. Try to push it. Take water in bucket and try to push it. What will happen? Will it compress or will it come from the spaces which are present? It will come, right? It will come and spill over. That means it is incompressible, so that whenever you add two chemicals, generally these processes are variable volume systems. Okay, so that is one thing. So now we have understood, okay, in a reaction there might be change in the volume, or volume of the system may remain constant. And we know for the gas phase how to calculate, and for the liquid and other phases how to calculate. So whenever a chemical reaction is given, what is your job? Your job is to check the coefficient of products and coefficient of reactants. Compare it whether they are equal or not, and you can get a preliminary estimation whether the volume of the system is changing or not. Now second part as an engineer is, अगर change हो रहा है, if there is a change, how to quantify it? कितना change हो रहा है, how to quantify it? What are the ways? So in that case we need some formulas to get what is the change, and there we talk about fractional change in volume. Fractional change in volume. So here it is defined as epsilon A, and it is fractional change and change with respect to initial. So we take reference as the initial volume. When conversion, that is XA, what is conversion we will discuss. We already have talked in previous class, is equal to 0. And when conversion XA is equals to at time t, that means entire reaction has happened. So conversion is 100% ideally. Conversion XA is equal to 1 minus volume conversion is equal to 0. So what we are comparing? We are comparing, okay, what is the volume at the end of the reaction and what is the volume at the start of the reaction. We take the difference, and that difference is again divided by the reference value, that is what is initial one, and this is gives you what is the fractional change. This is the change, and when we divide it gives you fractional change, correct? So for constant temperature and the pressure, we know n is proportional to the volume, so we can replace this volume with the number of moles. So total number of moles at Xa equal to 1 minus total number of moles at Xa equal to 0 divided by total number of moles at Xa equal to 0. Correct? This gives you fractional change in volume. Most important thing that you should keep in mind, it is always defined for limiting reactant. This we have covered how to calculate limiting reactant. Limiting reactant. And very important, this is defined when we have 100% conversion. Of what? Of limiting reactant. So defined for limiting reactant and 100% conversion of chemical reactant. We will solve one question that will help you to understand the epsilon A. So if you have any doubts, you can ask me. I'm here, and then we will solve question. So write down one question if there are no doubts. I have a reaction which is a gas phase reaction. So gas phase reaction, A plus twice B gives you thrice C plus 4 times D. This is a gas phase reaction and I have everything in gas phase. Every reactant in gas phase. Okay. And the question is, I have used equimolar amount of A and B. So A and B are the reactant. I have used equimolar amounts of A and B. That means in the initial reactor, I took equal moles of A and equal moles of B. Okay. So for this reaction, I want to calculate what is the epsilon, that is fractional change in volume. First of all, you need to see it is a gas phase reaction, and I said gas phase reactions are generally involve change of volume. You can also refer here and see 3 plus 4, which is product stoichiometric coefficient, is not equal to the stoichiometric coefficient 1 plus 2 for the reactant. There is indeed change in the volume. So it is written equimolar amounts of A and B were taken. That means number of moles of A are equal to number of moles of B. So assuming or take basis as 100 mole. 100 mole is the basis which has A plus B. You can take 1 mole, you can take 200 mole, no issues. It is the basis. Okay. So in this 100 mole, equimolar amounts of A and B are present. That means number of moles of A are 50 and number of moles of B are 50. Equimolar means the mole fraction in this is equal. 50% is A, 50% is B. So species A, B, C and D, time t is equal to 0, time t is equals to t, where the conversion is 100%. Can you tell me what are the amounts at time t equal to 0? 50 moles of A, 50 moles of B. See, it is not written that there is a presence of product at the start. That means it is 0. The feed is pure and it has A and B. At time t is equal to t, that is at time when conversion is 100%, we need to find out what will be the amount. So what is the definition of fractional change in volume says? Can you go here and check? It says fractional change in volume is defined for limiting reactant at 100% conversion of limiting reactant. So there are two things. One is to find out limiting reactant, and second is 100% conversion of limiting reactant. I am writing LR. So what is the limiting reactant? How will you calculate? In previous class I told you we need to divide the number of moles that are present at initial stage with the stoichiometric coefficients. That means I need to calculate, for example, ratio R1, ratio R2 for ratio A, for example, for A, and ratio B. We need to calculate number of moles of A at start divided by stoichiometric coefficient of A number of moles of B at the start divided by stoichiometric coefficients B, right? So can you tell me, number of moles of A at the start is 50, divided by its stoichiometric coefficient is 1, number of moles of B at the start equal to 50, and stoichiometric coefficient is 2. That means this is 25, this is 50. Which one is lesser? Lesser is B. That means this is my limiting reactant. This is the question which is frequently asked in GATE exams. How to find the limiting reactant. Similar concepts are being used in chemical process calculation. So if you prepare here, it will be helpful for you to prepare for the other courses. Right? So we have figured out what is the limiting reactant, and that is B. Now what the definition says, 100% conversion of limiting reactant. 100% conversion of B means all the 50 moles of B converted to converted to give the product. That means when there is a 100% conversion, how many moles of B will be present? 0. Earlier there were 50. All 50 converted to all 50 converted to product, so there will be 0. Now from the reaction you can also calculate, if 1 mole of B, if 2 moles of B reacts, 1 mole of A reacts. That means the number of moles of A that are reacted is half of the number of moles of B. So अगर इसका 50 moles react हुआ है तो A का कितना होगा? It is half, that is 25. So 25 react हुआ, what is remain now is 25. So I'll write such that here it was 50 present minus all 50 reacted, so there is no B present. Here 50 were present, 25 reacted, and 25 are present. Now if 1 mole of A reacts, it gives 3 moles of C. So 25, if they reacts, it will be 75, and similarly D will be 100. D will be 100. So what are the total moles at the start? NT total at the start equals to 100, and NT at the end when X conversion of limiting reactant, that is B, is 100%. So how many moles are there? 25 plus 75 plus 100. So total is 200. Now you just substitute the values here in this equation. Total number of moles at the end are 200. Total number of moles at the start were 100 divided by 100. So it is giving you epsilon B, which is equals to 2. Right? So epsilon B you can easily calculate. So with this example, you can see you can calculate the total number of what is the fractional change in the volume. Any doubts in this question? You can ask me. Correct. So we have calculated how what is the fractional change in the volume. Now same reaction, what I'm doing, I'm changing the initial composition. I'm changing the initial composition. So question number 2, the reaction is same. I am changing the initial mole fraction, and now in the reaction, A plus twice B gives you thrice C plus 4 times D. Here I am saying initially I have initially I have 30% of A. It can be anything. You can just change the values and get new values. 40% of B, correct? 30 plus 40 is 70. What is remain is 30%. So 10% of C and 20% of D. 20% of D. Now can you calculate what is the limiting reactant? What is the limiting reactant? And what is the fractional change? So you know, take 100 mole at start. So at t is equal to 0, t is equal to t, when xa is equal to 100 or whatever is the limiting reactant is 100. First of all, our aim is to find limiting reactant. So limiting reactant is 100 moles of A at the start. So at t is equal to 0, A, B, C and D. How many moles of A will be there? 30 moles. B is equal to 40 moles. C is equal to 10 and this is 20. So total number of moles is equal to 100. Now you calculate the ratio RA and RB as what we calculated last time. It is 30 divided by 1 and 40 divided by 2. So which is lesser? 20, right? So limiting is B is the limiting. B is the limiting. What does that B tells? B tells you, okay, whatever is the thermodynamic condition, 100% of B will react. There will be some leftover of other chemicals because B is something that is limited. B is something that is limited. For example, I want to prepare tea. I need water, I need chai patti, I need sugar, right? If I have a limitation of water, what will happen? In that case, and I'm saying, okay, I have only 1 cup of water. No matter tea, how much of tea leaves I have, how much of sugar I have, I can prepare only 1 cup of tea, right? That is the physical significance that tells you, okay, this is my limiting factor, which is telling me, okay, you- which is telling me what is the limitation, what is the maximum limit I can produce. Okay, so we have calculated limiting. Now you just tell me, okay, what are the number of moles of different components at time t is equal to t. So the definition tells number of moles at 100% conversion of limiting reactant. In our case it is B. That's why we will have the formula nt at xb is equal to 1 minus nt at xb is equal to 0 divided by nt at xb equal to 0, which will give you epsilon b, which will give you epsilon b. So we had 30 initially, 40 here, 10 here, 20 here. I am saying 100% conversion of limiting reactant. So 40 moles are there, all of them converted into product. So what is remained is 0. If B is reacted fully, the number of moles of A that will be reacted is 40 divided by 2 because uska half react hota hai, correct? So 40 divided by 2 is 20, and then there will be leftover. Okay, so this is 10, sorry. For C, जितना A का रिएक्शन होता है, whatever number of moles are reacted, you just multiply it by 3. So 20 into 3 is 60. Earlier already there were 10 moles were present. So those will be added here and total will be 70. That means my feed is not pure. It also has some chemical product that is present in the reaction. Then whatever number of A into 4 is giving you number of moles of D that are formed. So 20 into 4, that is 80, plus initially 20 were present, so it is giving you 100. Now you just sum it, 180, right? So what is this value? 80 divided by initially 100 were present. So zero point 0.8, that means what has happened? What has happened here? Epsilon has reduced. That means fractional change in volume is zero point 0.8 here. With respect to initial, this is the change. 80% change is happening. Sorry, this 8.8 is equals to 80% of initial. Okay. So now from this reaction, what did you observe? What did you observe? Question number 3. What are the factors that affects the epsilon value? Question number 3 on your screen. Factors affecting epsilon A. What are those factors? First you can see is the stoichiometry. First factor is the stoichiometry that is affecting. Then second thing is what is the composition of feed? What is the composition of feed? You can see earlier I had different composition at the start. In two problems that we have taken, we had different amount of initial chemicals, and accordingly we got different values of epsilon B. So along with stoichiometry, initial composition is something that affects. Correct? Initial composition that affects. Now can you calculate what will be epsilon A in question 1? Yes, correct. Question number 1. What we calculate was epsilon B. Yes, it was epsilon B because B was limiting. Can you calculate for the same question what is epsilon A? We know that fractional change in volume is defined for limiting reactant, but can we calculate epsilon A? Indeed, we can calculate epsilon A, though it will not be used in calculating the conversion and other parameters. So in this reaction, if I am considering, I will just erase this part. Can anyone calculate what is epsilon A? Fractional change in volume with respect to A. It means 100% conversion of A that has happened. 100% conversion of A that has happened. In epsilon B, what we did? We converted B into product and we assume that B has converted completely. Now we are assuming A. So how much A are present? 50. Convert it. 50 were present. 50 has converted. Remain is 0. If 50 moles of A reacts, then how many moles of B will react? 100. Correct. So initially 50 were present. 100 reacted. So what is remain is minus 50, right? Then 50 moles of A. So how many moles of C will form? Thrice of that. So it is 75. 75 plus 0. 0 were the initial values. We were not having any C in the feed. So 75. Similarly D. It is 0 plus 100, which will give you. Now you calculate. It is supposed to be 200 because per mole of A there are 4 moles of D are being formed. So 50 mole के लिए it will be 200. Yes. So this is what 275 minus 50, 225. There are mistakes. Can you find out what are the mistakes? What are the mistakes? We are saying 50 moles of A reactate. So 100 moles of B will react and C will be equal to 3 times of A. So 3 times of A is 50 into 3. It is 150. And here it is 200. So this value would be 150. So total is equals to 300. Now you can see earlier initially we had 100. Now these are 300. So what is the fractional change with respect to A? 300 minus 100 divided by 100. So it is 2. 200 divided by 100, which is 2. So epsilon A is equals to 2 and epsilon B is equals to, what was that value? It is supposed to be 1. Epsilon B is 1. So we can calculate epsilon B and epsilon A. Epsilon A and epsilon B we can calculate for these reactions. Understood? Should we move forward? Okay, so now we will be having just a small part. This you must have derived. So total number of moles at the start is equals to nt naught, which is equals to na naught plus nb naught plus nc naught plus nd naught, and at the end it is nt, which is equals to na plus nb plus nc plus nd, right? And you know, if xa is the conversion of a, how to calculate xa? Conversion is basically how much mole has converted. So xa will be equals to dna by, it is dna, okay, by na naught. That means it is change in number of moles per unit initial value. Whenever we are taking reference, it is always initial value. Na naught represent na reacted, so this is number of moles that are present and with respect to initial. So what we are doing, na was the initial amount, na is the, na naught is the initial amount, na is the current value, initial amount, initial moles, na is the current moles, and this is initial. So we are taking, okay, what was the earlier value, what is present, so that difference will give you the moles that are reacted upon what were the initial. So that will give you the conversion. So conversion for a is na naught minus na divided by n naught, which is equals to 1 minus na by na naught. This you have covered in the class. Similarly for b, that is a reactant, xb is equals to, you can write the same equation. And for xc, which is the product, earlier those were nc naught, okay, what are the present values, that is nc, okay, and then with respect to nc naught, so with respect to nc naught, what is the change, correct, is giving you xc, will give you xc, right? So we can write na is equals to, using this equation, na naught 1 minus of xa, and nc is equals to n c naught 1 plus xc. And we also know the extent of reaction, na naught xa divided by a is equals to nb naught xb divided by b is equals to nc naught xc divided by c is equals to nd naught xd divided by d. How did you get this? Minus ra by a is equals to minus rb by b is equals to rc by c is equals to plus rd by d, right? From this equation you get what are the converted per unit, this thing, correct? So now using this formula you can convert nc is as nc is equals to nc naught plus nc naught into the xc, oh it is, plus nc naught xc divided by nc naught into xc, and nc naught into xc is this, which is equals to nc naught plus this term will be na naught xa divided by c into, correct, opposite, a will be in division and then there will be multiplication of c. Similarly we can write for all these components and we can get final expression as nt is equals to nt naught, right? You just substitute this value here and you are supposed to get total number of moles at the end, which is equals to nt naught plus na naught into xa and there will be C by A plus D by A minus B by A minus of 1. If you write, it is NT naught plus NA naught XA, correct? XA. This is C plus D minus A plus B divided by A. So what is this? This is what we have calculated, right? The difference between stoichiometric coefficient of product and reactant, that is delta N. So delta N is this, right? And delta N divided by A is called as del A. A is considered as a limiting reactant for the time being. So NT is equals to NT naught plus of Na naught divided by Na naught into XA, correct? Na naught into XA into this value, which is delta A. And what is delta? Delta A is this value, right? So we had the formula epsilon A is equals to NT minus NT naught divided by NT, that is volume at T minus volume at T naught divided by volume at T naught, right? So just substitute the value of NT here. You are supposed to get NT naught minus NT naught plus Na naught XA del of A, right, divided by NT naught. So this will get cancelled. I'll be having Na naught divided by NT naught into XA del of A. So this is what is giving you what are the number of moles initially present for component A divided by total number of moles. So this will give you what is the mole fraction. So we are calling it as YA, that is a mole fraction of A into XA into del A. XA into, wait, wait, wait. Anything missing? Yes. Yes. So this is correct, right? And we are assuming that when we calculate epsilon A, we are considering 100% conversion of limiting reactant. So XA is equals to 1, and hence you are supposed to get YA into the delta A and T, right? So this is epsilon A. So using this formula also you can calculate what is epsilon a, epsilon b, epsilon c, epsilon d and all, right? You can calculate those values because you know what are the number of moles initially present, Na naught or Nb naught or Nc naught, right? Here that we have seen, these are the initial moles. You just divide by the total number of moles and then multiply by delta n, multiply by delta n by a, that is this, correct? So can you calculate for first case where we had this? So epsilon a is equals to, what is ya? Ya is 30 divided by 100 into what is delta n? Delta n is 3 plus 4, sum of the stoichiometric coefficient of product minus sum of the stoichiometric coefficient of reactant. So 3 plus 4 7 minus of 3, which is equal to 4, divided by a is 1. So you are supposed to get this value, 3 into 4 divided by 10. Right? And then epsilon b is equals to 40 divided by 100 into 4 divided by 2. So 40 divided by 100 into, so this is, you can see epsilon b is equal to 0.8, and similar value we obtained using this method. Both the methods are giving you same values, right? Both the methods are giving you same values. Now you can also see, okay, epsilon a is equals to vt at 100% minus of vt naught divided by vt naught. This is for 100% conversion. That means vt naught into epsilon a is equals to vt minus of vt naught. So vt is equals to vt naught 1 plus epsilon a. So this is the value when there is 100% conversion of limiting reactant. And you know, as the number of moles increases, volume increases, and hence we can also write in terms of conversion. Okay, so here it would be for 100%. What if the conversion is not 100%? Then fractional change in the volume will be that conversion times. Okay, so this will be vt is equal to vt naught 1 plus epsilon a into x. So this is the value, this is the value. Similarly, for vt is equals to vt naught, we can also write in terms of epsilon b into xb. So these are the various formulas that you can use. So now what is the physical significance? The question here is, what is the physical significance of epsilon a? So we know it is a fractional change with respect to initial. Initial is 1. Initial is v t naught. With respect to that value, what is the fractional change? So if fractional change is 0, that means volume has not changed. So for example, the question is for constant volume reacting system. Constant volume reacting system, what is the value of epsilon a? So we know volume is constant, that means Vt naught is equals to Vt, hence epsilon A is equals to Vt naught minus of Vt divided by Vt naught, right? And hence you should get zero value. That means zero value of epsilon signifies that volume has not changed. Volume has not changed. So epsilon A is equals to 0, that suggests that constant volume reacting system. Similarly, if volume increases, that means the product, this Vt minus of Vt naught, this is the final answer, will be greater than, it is positive, right? Volume has increased, that means Vt is higher and Vt naught is lesser, so the difference is positive, epsilon A will be greater than 0. So whenever somebody is asking you if epsilon A is greater than 0, that means it is representing that volume has increased, and hence epsilon A less than 0 means decrease in volume. That tells you what? Compression. So this is the question that may come, right? So whatever we are discussing, this is for batch system. For continuous system, instead of having a number of moles, we will be having molar flow rate. So in batch system, I'm writing, if you have Na is the number of moles of A, continuous system will be having Na naught per unit time, which will give you volumetric flow rate Fa naught per unit time. This is a rate, is equals to moles per unit time, for example in second, here it is moles. All formulas will remain same. Here it will be the flow system where it is happening with respect to time, it is changing with respect to time, flow, and hence why we need to convert the flow rate. So xa is equals to, here for example, 1 minus of Na divided by Na naught, then here xa would be equal to 1 minus of Fa divided by Fa naught. For products, xb is equals to 1 plus Nd, for example, divided by Nd naught, and here xd is equals to 1 plus Fd divided by Fd naught. This will give you conversion. Similar thing is happening here. Now we will solve one question based on this concept. The question I'm having, okay. Yes. So this is the question. For question for an irreversible gas phase reaction, for an irreversible gas phase reaction, that means the direction is only towards the product, irreversible process. The equation is given at A is giving you 5b. So this reaction is decomposition reaction, which is irreversible reaction. This reaction is happening at constant temperature and pressure. constant temperature and pressure, and the presence of B is 0 at the start. Initially, the feed has B equal to 0. That means no B is present, product is not present. However, there are inert present in the system. Inert present in the system. That means A plus inert, which are not reacting but present. A plus inert is giving you 5B. 5B. If at the end of the reaction final volume is thrice the initial volume, that means the system cannot go beyond 3 times of the initial volume. There is expansion, but that expansion cannot go beyond 3 times. So initial volume into 3, which will give you final volume. What is the minimum? What is the minimum amount of inert present at the start? We need to calculate in mole fraction. What is the mole fraction of inert at the start? So the question is there on your screen. Use the formulas that we have derived, we have understood, and try to solve this question. I'll give you 5 to 10 minutes to think and solve this question. Okay? Okay, so we will solve this question that is present on your screen. What does the question says? We have a reaction and for which the equation is given. Then here we have there is no B present in the feed and only inerts are present, and at the end I can have maximum 3 times of the initial volume. So I know what is the initial volume and what is the final volume. Initial and the final volume I know. So I can use this to get the value of fractional change, right? So what is the formula? V is equals to V naught 1 plus epsilon A into the XA, and when there I'm saying final, XA is equals to 1. Okay, so V is equals to, that is 3 times of V naught is equal to 1 plus epsilon A. So I will get epsilon A as 3 minus 1, which is 2. So I got the value of epsilon A, which is fractional change in volume. Now using this, I know I have a formula. I can get epsilon A is given as del of A into Ya naught, del of A into Ya naught, right? So what is del of A? Del of A is basically delta n divided by A, which is 5 minus 4 1 divided by 1, which is equals to 4. So this is 4, this is 2, Y naught is here. So Y naught is equals to 0.5. That means at the start I had 50% of A. That means what is the minimum amount of inert that is present is 50%. Therefore amount of inert or volume fraction of inert present is equals to zero point 0.5, right? Zero point 0.5. So this is what is the solution of question. So if you have any doubts, you can ask. I'm here, and then we will close the session. So if you do not have any doubts, we will close this session and we will meet in the next class. Thank you so much.